Welcome to our little curious podcast, Hidden Synapses. For centuries, the mystery of what determined sex puzzled scientists. Was it the mother? The father? The environment? Then, in a quiet laboratory, Nettie Stevens peered into a microscope and saw something no one had noticed before: tiny chromosomes that held the answer. This is the story of the woman who cracked one of biology's biggest codes, only to have history overlook her. The groundbreaking discovery of sex chromosomes emerged from the dedicated work of Nettie Stevens, a scientist who overcame significant gender barriers in the early 1900s to make one of genetics' most fundamental contributions. Born in 1861 in Cavendish, Vermont, Stevens entered the scientific world at a time when women's participation in research was not just discouraged but often actively prevented. Despite these societal constraints, she demonstrated exceptional academic abilities, particularly in mathematics and science, areas traditionally considered unsuitable for women of her era. Stevens's path to scientific achievement was marked by determination and resourcefulness. Unable to directly pursue higher education due to financial constraints, she first worked as a teacher to save money for her studies. This practical experience eventually enabled her to enroll at Stanford University, where she earned both her bachelor's and master's degrees in biology. Her academic journey then led her to Bryn Mawr College for doctoral studies, where she quickly distinguished herself through her meticulous research methodology and innovative thinking. The scientific community of the early 1900s held various theories about biological sex determination, with many researchers believing that environmental factors or some form of combined parental inheritance determined an offspring's sex. Stevens approached this mystery from a different angle, focusing on the cellular level through detailed chromosomal studies. Her breakthrough came through careful examination of mealworm specimens, where she observed a distinct pattern. Male mealworms possessed one large chromosome, X, and one notably smaller chromosome, Y, while females consistently showed two large X chromosomes. This observation led Stevens to propose a revolutionary concept. Sex determination was not controlled by environmental conditions, but by specific chromosomes. She demonstrated that sperm carrying an X chromosome would result in female offspring, while sperm with a Y chromosome would produce male offspring. This discovery established the fundamental principle of chromosomal sex determination that we now know as the XXXY system. Despite the significance of her findings, Stevens faced several obstacles in receiving proper recognition for her work. Edmund B. Wilson, a male colleague who reached similar conclusions around the same time, often received more credit for the discovery. This occurred even though Stevens was the first to provide direct evidence of chromosomal sex determination. The scientific establishment's bias toward male researchers meant Wilson's work received more attention in academic literature and historical accounts. The impact of gender bias on Stevens's recognition was compounded by her tragically short career. Her death in 1912, after only about a decade of active research, prevented her from fully establishing her scientific legacy. This brief period in the field, combined with the prevalent gender discrimination of the era, resulted in her crucial contributions being frequently overlooked or minimized in scientific literature throughout much of the 20th century. Stevens's methodology was particularly noteworthy for its precision and thoroughness. She conducted extensive studies of various insect species, meticulously documenting chromosomal patterns and their relationship to sex determination. Her work went beyond simple observation as she developed theoretical frameworks to explain the patterns she observed, demonstrating both technical skill and theoretical insight that was ahead of her time. The passage of time has gradually brought increased recognition to Stevens's vital contributions to genetics. Modern scientists now acknowledge her as one of history's most important female geneticists, and her work is recognized as foundational to our understanding of chromosomal inheritance. The XXXY system of sex determination that she discovered continues to influence our understanding of genetics, development, and inheritance patterns across species. Stevens's legacy extends beyond her scientific discoveries. Her story serves as both an inspiration and a cautionary tale about the impact of gender bias in science. While her scientific acumen and dedication led to a fundamental discovery that we now take for granted, the historical undervaluation of her work reminds us of the importance of recognizing scientific achievements, regardless of the researcher's gender or social status. Her perseverance in the face of institutional barriers and her commitment to rigorous scientific investigation continue to inspire new generations of scientists, particularly women entering STEM fields. Nettie Stevens' discovery of X and Y chromosomes changed the way we understand genetics, evolution, and even medicine. Though her work was overshadowed in her time today, we recognize her as a true pioneer of biology. Every time we talk about XX and XY, we are talking about her legacy. Thank you for joining me on this journey through Nettie Stevens' life. If you enjoyed this episode of our podcast, Hidden Synapses, don't forget to subscribe and share. And if there's another underrated scientist whose story you think should be told, let us know. We'd love to explore it in a future episode.